582, section 8.3 is the inverse of a square matrix. Just a little bit of review of something that we finished off with yesterday. The end of the period yesterday, we were talking about the multiplicative identity matrix. And we said that it was the matrix that had all ones in its main diagonal, and then it had zeros everywhere else. So it looks a lot like reduced row echelon form. But remember, in reduced row echelon form, you can have like an all zero row at the bottom, or as long as the leading one is further to the left than the one below it, it doesn't have to go in that perfect little stair-step pattern with the main diagonal of all ones. So it is very similar to reduced row echelon form, and we'll actually use that idea to help us a little later on today. But an identity matrix is going to have all ones in the main diagonal and zeros everywhere else. It does have to be square, so it's going to be like a 2 by 2 or a 3 by 3 or a 10 by 10, whatever. It will follow that same kind of a pattern. The reason it's called the identity is because if you take a matrix and you multiply it by the identity matrix, you're going to get the matrix that you started with. And so we've got an example here of a 2 by 2 multiplied by the 2 by 2 identity. And when we go through and we do, you know, row 1 times column 1 and row 1 times column 2, row 2 times column 1, row 2 times column 2, we still come up with that exact same matrix that we started with. The idea of today's lesson deals with inverses. And it's called the inverse of a square matrix, so that gives us the first clue. If you're going to take the inverse of a matrix, it does have to be square. You must have a square matrix in order to have an inverse. So it would have to be a 2 by 2 or 3 by 3 or 4 by 4, something like that. There are matrices that you cannot find the inverse of, and so they're called not invertible. If your matrix is not invertible, it is also called singular, and that's a bold print term on the top of page 583. Where that pops up a lot is on our calculator. Like, we'll put a matrix in our calculator and ask the calculator to find the inverse of it, and we'll get an error message, and it literally says error singular. And that's what it's telling you, is that this matrix doesn't have an inverse. It's not invertible. If you can find the inverse of a matrix, if it is invertible, then it's called non-singular. And again, those are bold print terms on the top of 583. Now, something else that is true about inverses, and they tell us this at the beginning of example 1 on page 582, is that if A and B are inverses of each other, then when you multiply A times B, you'll get the identity matrix, and when you multiply B times A, you'll get the identity matrix. We mentioned in section 8.2 that A times B doesn't have to be the same thing as B times A. And so that's why they say in both orders, A times B and B times A, you'll get the identity matrix. So on the homework, they will give me two matrices, and they'll say these two are inverses of each other, prove it. And how do we show that they're inverses of each other? All we would have to do is take the two matrices that they gave me, multiply A times B and show that we get the identity matrix, multiply B times A and show that we also get the identity matrix. And so then we could just say, since A times B equals B times A equals the identity, then they're inverses of each other. They won't always give me the inverse. Sometimes they'll give me the matrix and ask me to find the inverse. So if I want to find the inverse of, let's start with a 2 by 2. If I want to find the inverse of a 2 by 2 matrix, there are several different ways that we can do that. On page 584, they give me a matrix in example number 2, and they give me 1, 4, -1, -3, and ask me to find the inverse. They tell me that if I will put my matrix on the left-hand side and put the identity matrix on the right-hand side for step number 1, then in step number 2, I want to use elementary row operations to row reduce that left-hand side, my matrix. I want to row reduce it to the identity matrix. And again, we talked about at the top of the page that the identity matrix is not reduced row echelon form, but that it has a lot of the same characteristics. So that will give you something to work towards when you're trying to do this. It's the same elementary row operations and the same process that we were using back when we were putting something in reduced row echelon form. So we can use that as a little bit of a guide to help us there. Okay, so then step number 3, the answer that I get once I create that identity on the left-hand side, the matrix that is sitting on the right-hand side will be my inverse. So let's look at an example of that. They had given me the matrix 1, 4, negative 1, negative 3, so I'm going to put that on the left-hand side, and I'm going to put the 2 by 2 identity matrix on the right-hand side. And I'm going to use elementary row operations to create the identity matrix on the left, so I need 1, 0, 0, 1 over here. So I already have 1, that's good, so let's work on making this a 0. If this is a negative 1, then I would need a positive 1 to make it a 0, and I have 1 in row number 1, so I don't have to create one. Let's go ahead and add row 1 and row 2 and put it in row 2. So I added row 1 and row 2 and put it in row 2. So now down here I've got my 0, and hey, I got a freebie over here. I also got a 1. That doesn't always happen, but it's nice when it does. And notice this is changing over here. This is no longer the identity matrix over here. That's my goal. I want that to happen. Okay? So now I've got 1, 0, 1. I need this 4 to be a 0. So for the 4 to be a 0, I would need a negative 4. I don't have one, so I'm going to have to make one. So I'll multiply the second row by negative 4 and add it to the first row. So second row times negative 4 added to the first row, created the identity matrix. And so they told me the identity would be on the left and the inverse would be on the right. So this is my inverse. Negative 3, negative 4, 1, 1. That's one way that you can find the inverse of a 2 by 2. If you are not a huge fan of elementary row operations and putting something into an identity matrix like we do for reduced row echelon form, here's another way that you can find the inverse of a 2 by 2. Let's take that exact same matrix that we just had, 1, 4, negative 1, negative 3, and let's look at a second way that we could find the inverse of that 2 by 2. To do it, I'm going to need to jump a little bit ahead to the idea of a determinant. They haven't taught us about determinants yet. We'll do that later on in this chapter. But the determinant of a 2 by 2 is fairly straightforward. If I want to find the determinant, and we'll represent that with a capital D, if I want to find the determinant of a 2 by 2 matrix, I'm going to take the main diagonal and multiply A times D, and then I'm going to take the alternate diagonal, multiply B times C, and then just subtract those two products. So my determinant will be AD minus BC. So for this matrix that we had, if I found the determinant, I would do 1 times negative 3 minus 4 times negative 1. So 1 times negative 3 minus 4 times negative 1. And that would give me a determinant of positive 1. All right, then step number 2, I'm going to use this formula for the inverse of a matrix. It is 1 divided by the determinant, that answer that we just got, times the matrix that's been altered. And if you'll notice, here's how they altered it. They took A and D and they swapped places. B and C are where they were initially, but they are the opposite sign of what they were initially. So for my matrix, if I follow this formula, I'm going to do 1 divided by the determinant. We just got 1 for that determinant. I'm going to take A and D and have them swap places. So instead of 1, negative 3, I'm going to have negative 3, 1. B and C are going to stay where they are, but their sign's going to change. So instead of positive 4 and negative 1, I'm going to have negative 4 and positive 1. So now when I do this scalar multiplication, 1 times negative 3 is negative 3. 1 times negative 4 is negative 4. 1 times 1 is 1. 1 times 1 is 1. So this would be my inverse. And sure enough, if I go back and look a second ago, we've got negative 3, negative 4, 1, 1. That was the exact same answer that we got down here when we used that other method. Okay? So if I need to find the inverse of a 2 by 2, I could do it by either of those methods. I also could do it on my calculator. I'll show you how we put inverses in our calculator in just a minute. All right, so why do I need the identity matrix and why do I need inverse matrices? Well, we can use them to help us solve matrix equations and to help us solve systems of equations. All right, let's look at this example. I have a matrix equation here. I have one matrix times some unknown matrix is equal to another matrix. We mentioned when we had an example like this previously that it's a lot easier if I represent the matrices with letters and I solve using the letters. So let's do that. I'm going to call this matrix A and I'm going to call this matrix B so I don't have to deal with all of those numbers. All right? So if I'm trying to get X by itself, I need to undo matrix A. We said a little bit ago that the inverse of a matrix would undo it. So we could say the inverse of matrix A times matrix A. And we learned earlier today that when you multiply a matrix times its inverse, you get the identity matrix. All right. We also said at the beginning of the lesson that if you take the identity matrix times any other matrix, you will get that other matrix. So, hey, I got X by itself on the left-hand side. That's what I wanted to do. How did that alter the right-hand side? Well, of course, what I do to one side, I always do to the other. So if I'm going to multiply the left-hand side by the inverse of A, I'm going to multiply the right-hand side by the inverse of A as well. So that tells me that to find X, I need the inverse of A times B. So let's simplify it down to two steps. Step number one, I'm going to need to find the inverse of matrix A. That's what we were just doing a second ago. You could do it by either method, whichever one you liked better. Step number two, I'm going to multiply the inverse of matrix A times B. This little guy right here, circle it, star it, highlight it, do something to it, because this is the key. It has to be in that order. You have to do the inverse of A times B. You cannot do B times the inverse of A or you will not get the right answer. Remember, we saw in section 8.2 that A times B is not the same thing as B times A. The order matters. Okay? So let's go back to our equation that we were trying to solve. We called this matrix A. So step number one, we got to find the inverse of matrix A. I'm going to use that second method for finding the inverse that we just looked at. So I'm going to go through and first find my determinant. Negative 2 times 6 is negative 12. Minus 3 times negative 5 is negative 15. So minus a negative 15 would be plus 15. That gives me a determinant of 3. Then I'm going to use that formula. And the formula for the inverse was 1 over the determinant. So we'll put in that 3 that we just got. A and D switched places. B and C stayed where they were, but their signs changed. This was a negative 5, now it's positive. This was a negative 3. This was a positive 3, and now it's negative. So I can do my scalar multiplication. 1/3 of 6 is 2. 1/3 of 5 is 5/3. 1/3 of negative 3 is negative 1. And 1/3 of negative 2 is negative 2/3. So there's my inverse. So we've done step number one. Step number two is take that inverse and multiply it times B in that order. So I'm going to take that inverse we just created and multiply it by matrix B. It's a 2 by 2 and a 2 by 2, so their inside numbers are the same, so I can multiply. The outside number tells me that I'm going to have a 2 by 2 as my answer. So we'll go through and we'll multiply our rows and our columns, and we come up with our solution. Now, this is entirely optional, but you know how anytime you solve an equation, you can always go back and put your answer in and check it and make sure that it's right. You know you got it right before you ever turn your test or quiz in. You can do the same thing with a matrix equation, because you can go through and say, okay, if this was matrix A that we started with on the top, and this is the answer that we just got for X, when I multiply A times X, I should get B. And sure enough, when I multiply, I do get matrix B. So then I know that it's correct. So we've seen how we could find the inverse of a 2 by 2 and use it to help us solve a matrix equation or a system of equations that would be represented by that matrix, a system of equations with two unknowns. What if I had a system of 3 equations with 3 unknowns, or I had a matrix equation that had a 3 by 3 in it? That means that I'm going to need the inverse of a 3 by 3 to solve that, right? Now, if I'm trying to find the inverse of a 3 by 3, that means that I'm putting that in 1, 0, 0, 0, 1, 0, 0, 0, 1. We're talking like 10 minutes and half of a sheet of paper, right? When it comes to a test or a quiz, we just don't have time for that. Yes, on the homework we could do that, but in that type of a timed setting, we just don't have time to do the inverse of a 3 by 3. So anytime I ask you to do the inverse of a 3 by 3 on a test or a quiz, I will always allow you to do it on your calculator. So grab your graphing calculator and let's look at how you could find the inverse of a 3 by 3. I want to show you two different ways that you can do that. All right, you have a dedicated matrix button on your calculator. It is right here above x to the negative 1. So I'm going to do second x to the negative 1, and that takes me to my matrix menu. Now, you may have nothing on this screen, or you may have all kinds of things on here, but yours are almost definitely not the same thing as I have on mine. Perfectly fine. I'm going to choose one of these matrices. It doesn't matter which one. You could choose A, B, C, D, E, F, whichever one. I'm going to stay on A, and I'm going to go over to Edit. So I'm telling it to edit matrix A. If I went down, I could edit matrix B. Go down again, I could edit matrix C. Okay, so I'm going to choose that first one, and then I can tell it the order that I want. So we're going to put in a 3 by 3. So no matter what you have there already, if you hit 3, enter, 3, enter, it will set up a 3 by 3 matrix for you. And let's put in this matrix 2, 3, 1. So you're going to hit 2, enter, 3, enter, 1, enter. And then it'll jump down to the next row for you. 3, you also can use your arrow keys to toggle around in here. So if you want to go through that way instead of hitting enter, you can. But on that second row, you've got 3, 3, 1. And then on that last row, you've got 2, 4, 1. All right, so once you've got your matrix entered, let's quit out of that. So second quit. I'm going to go back to matrix again. So second x to the negative 1. And this time I'm going to choose names. And wherever you just put that matrix, I put mine in A, but you might have put it in B, C, D, something or another. I'm going to choose A since that's where I put mine. So I'm back on my home screen, and when I put in matrix A, it knows what I'm talking about. It knows that 3 by 3 that I just put in. Here's my inverse button right here, x to the negative 1. So if I hit that and hit enter, it takes it a fraction of a second to calculate the inverse of matrix A. Whereas it's going to take me, half a sheet of paper kind of thing. So here's our inverse for matrix A. Here's when I would want to use that menu. On a test or a quiz, to try to speed things up for you, a lot of times I'll give you, this is matrix A, this is matrix B, this is matrix C. I'll give you 3 matrices, and then I'll go through and say, okay, add A and B. Multiply A and B, find the inverse of A, find the determinant of B, so that you don't have to keep typing in the matrices over and over again. So if you'll come to this menu and go ahead and put in matrix A, B, and C, then you can go and just tell your calculator to add them, subtract them, multiply them, find the inverse of them, whatever it is that we're trying to do. Okay? If you're not in that type of a setting, if every single problem that you do, the matrix is changing, then there's actually a little faster way to put in a matrix than what you've got here. When we got the new operating system on the 84, remember we got all these fun little function buttons and all the new menus? So if I'll do alpha zoom, that accesses that F3 menu, that is a dedicated matrix menu. So I can go right there and I can say I want a 3 by 3 matrix. I can tell it how many rows and columns, and it will put a blank one right there on my main screen. And I can just type in my numbers. That's really fast and easy if every matrix I'm putting in is different. So let's go through and put that same one in that we had a second ago. Don't hit enter when you put in your number. Like when I put in 2, if I hit enter, then it thinks that's the matrix I want it to evaluate, and it'll go with that. I have to use the little arrow buttons to maneuver around in this setting. So I'm going to have 2, 3, 1, 3, 3, 1, 2, 4, 1. And then I can still use that inverse button, and I'll still get the exact same answer. Okay. So 2 different ways that we can do them. It kind of depends on the setting you're in as to which will be faster and easier for you. So just for review, we looked at two different ways to do this. We went to second x to the negative 1, which was our matrix menu. We went over to edit, and we chose the matrix we wanted to edit. You could choose A, B, C, D if you have multiple ones to put in. We chose matrix A, and we told it we wanted a 3 by 3, and we put in our values. Then we quit out of that to go back to the main menu. We went back to matrix, and this time we left it in names, and we selected that matrix we had just created, and that put it on our main screen for us. And then we chose the x to the negative 1 button, and it gave us the inverse. The other way that we put this in was we did alpha zoom, which is our F3 button. We told it how many rows and columns that we wanted, and then hit OK, and it sets a blank one up on our screen for us. And then we can type those numbers in again. Remember to use your arrow keys as you're moving around. Don't hit enter until you're completely finished, and you'll notice that we get the same answer either way. Okay? All right, so now that we know how to find the inverse of a 3 by 3 on our calculator, let's look at example number 5 because we're going to need it there. So example number 5, they asked me to solve a system of 3 equations with 3 unknowns. And look at how they've used matrices to rewrite this system, okay? Down here, we've got a coefficient matrix. They've just gone through and pulled out 2, 3, 1, 3, 3, 1, 2, 4, 1. That's our coefficient matrix right there. We're multiplying that by our unknowns, so x, y, and z, and then that's equal to our constants over here, negative 1, 1, and negative 2. That is how I could write this system of 3 equations with 3 unknowns as a matrix equation. Because look what happens if I put this back together again. This is a 3 by 3, and this is a 3 by 1. Inside numbers are the same. I can multiply. Outside numbers tell me my answer is going to be a 3 by 1. It is right there. If I go through and I do first row times first column, I'm going to get 2 times x plus 3 times y plus 1 times z is equal to negative 1. That is exactly what that first equation is, right? So all they've done here is just rewritten the system by using matrices in that way. Now we're right back to the example that we did a few moments ago, right? Where we had a times x was equal to b, and we said step number 1 we had to find the inverse, and step number 2 we had to multiply the inverse times b. We stressed that it had to be in that order, okay? Exact same thing, only in that case we were working with a 2 by 2, in this case we're working with a 3 by 3. So step number 1, when I need the inverse of the 3 by 3, I'm going to get that off of my calculator. This is the exact one we just did in our calculator a moment ago. This was the matrix we put in. This was the inverse that we got out. Okay? Then step number 2, I'm going to take that inverse and I'm going to multiply it times matrix B. So if I take that inverse and multiply it times matrix B, this is the answer that I get. And you'll notice that that lines up with the x, y, z that we had set up over here for our unknowns. So that means that x is 2, y is negative 1, and z is negative 2. And that gives us yet another way to solve a system of 3 equations with 3 unknowns. Okay, so here is our homework for tonight. And be sure that you do number 21 on the calculator.